Hello, this is the second part of the module dealing with spatial autocorrelation. In the previous set of slides, I talked about the concept of spatial randomness and the two alternatives of positive and negative spatial autocorrelation. And we also focused on how to construct a statistic for spatial autocorrelation. And we saw that to do this right, we really need two parts. One part deals with attribute similarity, the other part deals with geographical or locational similarity. And we saw that the second part is formalized through spatial weights. And in this set of slides, I want to spend a little more time on spatial weights because they tend to be a major stumbling block conceptually when you have never been exposed to this. So I'll start by motivating why we need it and then go over some simple examples of spatial weights based on geography, some standard transformations, and then how we compare spatial weights, how we look at their properties. So why do we need spatial weights? And I want to come back to something I mentioned in the previous set of slides, namely that it's all about pairs of observations. We're really trying to eventually model interaction. But we're doing this in a very poor situation because we don't actually have interaction data. Now, some of you may be familiar with New York taxi cab data or things of that sort, where you have the actual interaction data. But in the settings that we will be analyzing in this course, we don't. We have a simple cross-section. Let's say the cross-section has n observations, but then we have all these pairwise interactions. And if you assume symmetry and you take out self interaction, then we have n times n minus 1 divided by 2 pairwise interactions. So there is no way, no matter what fancy statistics you use, there is no way you can measure that many pairs of interactions with a single cross-section. That is the fundamental problem. That's the fundamental problem of cross-sectional analysis. If you have flow data, it goes away. If you have time and space, it goes away to some extent, not totally. For example, just to give you, show you how bad this is, in North Carolina, there are 100 counties. So that means that there's a total of 5,000 pairwise interactions which we're trying to model, which we're trying to quantify with only 100 observations. You can't win this fight. So how do we solve this? We have to simplify it. We have to impose structure. And the way we impose structure is to limit the number of interactions that we deal with. Basically, that's what we're doing. So because the modeling of interactions suffers from what is called the incidental parameter problem. And the incidental parameter problem is a classic problem in statistics and econometrics, where the number of parameters that you need to estimate increases with the sample size. Some of you who may have had econometrics know about heteroscedasticity, which is where the variance of the error term is different for each observation. So if you really want to estimate that variance for each individual observation, you're out of luck. You can't resort to large sample logic because the larger the sample, the more of these variances you have to estimate. That's the incidental parameter problem. Now here we have it in the square because as our sample size grows, the number of interactions grows with n squared. So this is a race we cannot win. So the only way to deal with it is to give up on trying to estimate all the interactions and to simplify the problem by imposing some structure. And in essence, that structure boils down to saying we will ignore the interactions between certain pairs of observations. And so which are the ones that we will then focus on? Those are our neighbors, which will be formalized in the spatial weights. So the spatial weights are constructed to exclude interactions. If you have spatial weights that involve all the pairs of interactions, they're basically not good spatial weights for exploratory analysis. A lot of people wonder about that. There's a lot of attraction to using inverse distance between all the pairs of observations. That may be fine in an econometric model, but it's not good and not powerful in an exploratory analysis. In an exploratory analysis, you want to find evidence that the null hypothesis doesn't hold. And the null hypothesis is spatial randomness. And so you want this evidence to be as strong as it can be by looking only at the interaction with a few neighbors. So if that interaction with a few neighbors is already systematically stronger than it would be under randomness, then that definitely will be the case when you look at even more neighbors. So the point of the spatial weights is to constrain the number of neighbors. So we have what we will see later, a sparse matrix, meaning a matrix with lots of zeros in it. And important in this context, and this is also something that is very different between, say, standard correlation analysis by means of a Pearson correlation coefficient and spatial correlation analysis, autocorrelation analysis. As we'll see in the next module, the value of the statistic as such is really not that meaningful, because remember, we're trying to deal with interaction, and we will model, so to speak, or formalize that interaction by this weights matrix, which constrains the interaction to only a few neighbors, and then some coefficient that measures the strength of that interaction. So the interaction is actually made up of two parts. One part is the weights matrix, the other part is the interaction coefficient, so to speak, that is multiplied by that weights matrix. So the actual interaction, or if you wish, the spatial autocorrelation, consists of two parts, the weights and the coefficient. So if the weights are small for the same interaction, the coefficient will be larger. Let's say your interaction is 100 and your weights are 2, then the coefficient will be 50. The opposite, if the weights are large, then the coefficient will be small. Again, with an interaction of 100 and the weights are 50, then your coefficient will be 2. So you can never interpret an spatial autocorrelation coefficient in isolation without knowing what the spatial weights matrix is. Very important concept, and this is often forgotten. The spatial autocorrelation is about two things: attribute similarity and locational similarity. We cannot possibly model all their interactions, so we simplify them by the spatial weights, which is fixed, and then we apply a correlation coefficient to that. So the scale of the interaction consists of a product of two terms. And in those of you who've taken econometrics know that's an identification problem. If you can measure A times B, then you can measure the product, but you cannot independently assess what A and B would be. For a large B, A becomes small. For a small b, A becomes large for the same product. Keep that in mind. Very important concept later on when we interpret the results of our tests. So here's a little example. An arbitrary set of 6 polygons. They share borders. So polygon 1 shares a border with 2, with 4, with 5, and then 5 shares with 3, and so on. So this is our generic layout of our polygons with common borders. Importantly, we can also represent this as a network or a graph structure. So the graph structure takes the observations, so 1, 2, 3, 4, 5, 6, as the nodes in the network, and the existence of a common border as a link or an edge in the network. So we have our observation 1 with a link to 2, 4, and 5. Then 5 has a link to 3, and 3 has a link to 6. So this is the network or graph representation of our layout in terms of the existence of borders or the existence of neighbors. And we'll get back to that at the very end when we look at characteristics of spatial weights. So with this structure in mind, we can actually create yet another representation of the neighbor structure in the form of a matrix. A square matrix of dimension equal to the number of observations, n. So it's an n by n positive matrix. We call it W, we've already seen that, and the elements are Wij. Now Wij means the weights for the neighbor definition between the pair I and j. So if I and j are neighbors, Wij is not 0. Notice how I'm purposely very vague. I'm not saying it's 1, it's 10, it's a million. I'm just saying it's non-zero. And this relates back to the point I just made, that the interaction is actually a product of a coefficient and a weights matrix. So Wij, j, non-zero means neighbors. If it's obviously 0, then there are not neighbors. And this is the simplification that I was talking about. We're putting constraints into the weights matrix. In this case, the constraint is to set the weight to 0, meaning beforehand we specify that I and j do not interact. Right? Then what do we do with the diagonal elements? So a matrix has diagonal elements in the middle. That's Wii. Is I a neighbor of itself? In this context, it is not. But this is purely a convention. So because it's not, Wii, the diagonal elements, are set to 0. There are some cases in the literature where self-neighbor relations are allowed, and then Wii can be equal to something like 1, but we will not consider those. So in our situations, in the spatial literature in general, the diagonal is typically set to 0. There's good reasons for that. One is that a lot of statistics rely on the sum of the diagonal elements. And so if these are set to 0, that's really easy to deal with. If they're not, say they're set to 1, then the sum of the diagonal elements grows with the sample size, which is usually not a good thing. So keep in mind, simple matrix, Wij is I a neighbor of j. Typically it's symmetric, then j is also a neighbor of I, but not necessarily with the same value for Wij. By convention, the diagonal elements, these here, are all set to 0. When there is no neighbor relation, we set the weights to 0 as well. So in our example, we'll see that in a second. So as I mentioned in the previous set of slides, so we have attribute similarity, spatial similarity. We combine the two. The spatial similarity, the easiest way to think about this is based on geography, but it doesn't have to be. As I mentioned before, it could be based on social networks, for example. Geography is easy, and there's basically two broad classes of spatial weights that are based on geography. One is based on common borders, which we call contiguity. The other way is based on distance, a distance measure. So we'll look at contiguity first. The easiest contiguity weights are so-called binary contiguity weights, because the weights are either 1 when there is a shared border or 0 when there is no shared border. So it's very simple. You have a neighbor relationship, 1, you don't, 0. So in our example, here we are. This is the matrix. As many rows as there are observations, as many columns as there are observations. Each row is the I and looks at what is the neighbor relation with the columns, the j. So we know diagonal 0. Now we look at row 1, observation 1, and column 2, observation 2. we look in our graph, we see a common border here, so we put a 1. Observation 1 in the row, observation 3 in the column, no common border, 0. Observation 1 in the row, observation 4 in the column, neighbor. Same for 5, for 6, there is no neighbor. So that constitutes the first row of the spatial weights matrix. Because in this case, simple contiguity is a symmetric relationship, this row is exactly the same as the first column. In other words, the matrix is symmetric. Same thing here. Now we look at observation 2, here in the corner. 2 has a connection to 1. Diagonal, none to 2. 3, no connection. 4, yes. 5, yes. 6, no. So this is how we construct our simple binary 0, 1 spatial weights matrix for our little layout of 6 observations. Okay, there's some complications with, remember I just kind of said common border, but common border can mean different things. And the easiest way to explain this is to look at a regular grid. And we're interested in defining the neighbors for the central cell, observation number 5. And these type of neighbors get names, and the names are by analogy to chess moves on a chessboard. So think about that, and then you will see what they mean. So the first definition is a neighbor is an entity that just has a common side, but not the corners, just the side. We call that a rook definition. So a rook on a chessboard moves forward and sideways, but not diagonal, right? So observation 5 has rook neighbors 2, 4, 6, and 8. Very important, there's 4 of them. Keep that in mind. Now, if you know chess a little bit, you know the piece that can move diagonally is the bishop. And that's a second definition of neighbor based on contiguity. Now the neighbor relationship is defined by only having a corner in common between the two. So the diagonal moves of the bishop. This is hardly ever used, and we actually haven't even implemented it in GeoDa because it's hardly ever used. Rook, common sides. Now, what happens if we combine these two criteria? And so think of chess. What is the piece that can move both up and sideways, up, down, and sideways, as well as diagonal? That's the queen. And so queen, definition of contiguity, common neighbors, has both the 4 that have a common side, as well as the 4 that have a common corner. Now, what's the difference here? With the rook and the bishop, we had 4 neighbors on a regular grid. With queen definition, we have 8 neighbors. So the number of neighbors changes with the definition of contiguity. That's something that you don't have in time series. In time series, if you're one period behind, there's only one way to define that. Here, there's multiple ways to define the neighbor relation. And that's why we always have to think of spatial autocorrelation as the combination of the coefficient and the weights, never as a coefficient by itself in isolation. That's something that's often lost out of sight in the beginning. Always keep these two together. And I'll stress that in the next module when we talk about spatial autocorrelation coefficients. So we have rook and we have queen. What does this look like in reality? Here's Solano County in the Bay Area. We have the rook definition, only the sides. Now, it's actually quite difficult for US counties to find examples where there's a difference between rook and queen contiguity. Oftentimes, this has to do with the precision of the GIS. For example, here, we have this little corner, which makes that this additional county is a neighbor when we use the queen definition. But when you think about it, this map, this base layer from a GIS, is a simplification of reality. There are actually very few instances in practice where the corners of two geographical entities meet. Of course, there's a four corners point in the west between Utah and Colorado and so on, but that's very rare. So this has often to do with the specificity of the GIS. In other words, remember the notion of scale on a map. If we have this little piece here that corresponds in reality maybe with a mile or a couple of miles, but if the generalization of the map says, well, that's too small to consider as an actual stretch of line, we just make it a point, then you have a difference between rook and queen. But if it was, in fact, a little line, then you wouldn't have a difference between rook and queen. So oftentimes, these differences can be tied back to some issues with the underlying GIS. And in the lab notes, I talk about that some more, how you deal with that in practice with some GIS problems. Okay, so that's for contiguity, common border, rook and queen. As I mentioned, the other broad category of weights, spatial weights, that are based on geography are based on the notion of distance. And distance is between points. Common borders is between polygons. But as we'll see, it's actually much more flexible than that, because we can represent a polygon by a central point, a centroid, or a mean point, an average of all the coordinates. So some kind of central representation, or even for a county, say the county seat, or for state, the state capital, which would be a point, and then we can compute the distances. Distance-based weights can be any function of distance, but remember Tobler. Tobler's law implies distance decay. So you have to make sure that your weights also imply distance decay. What does that mean? For example, you cannot use the distance as such, because the distance gets larger as points get further away, which would imply more correlation. We want the opposite, so we will use inverse distance, or distance to some negative exponential, instead of the actual distance. In most of the applications in practice, we will just be dealing on a critical distance and say neighbors are those pairs that are within a given distance band. So these are called distance band weights. We have to pick a critical distance, d. Then any pair of observations, ij, that have a distance between them that is less than the critical distance, they're neighbors. The others are not. One possibility here is that we find pairs, or actually observations, that have no neighbors within that critical distance. They're too far away from everything else. And those then become what we call isolates or islands. And there's a problem with isolates in spatial analysis, because spatial analysis is about interaction. So if you don't interact, if you don't play, so to speak, then you can't be analyzed. So the way we deal with these isolates or these islands is, for spatial aspects of the analysis, we remove them. For the others, we can keep them. I'll get back to that in a minute. So one way to ensure that every observation has at least one neighbor is to take the critical distance as the so-called max-min distance. What does that mean? So every observation has a nearest neighbor. The nearest neighbor is the other point, the other observation, with the shortest distance to our observation. So that distance, we call it the nearest neighbor distance. So if we look at all the observations and we look at all the nearest neighbor distances, if we take the largest of this, the maximum of the minimum of the nearest neighbor distances, that distance ensures that every observation has at least one neighbor, because the one with the largest nearest neighbor distance will have its neighbor, and everybody else will have one or more neighbors. So that's a criterion to pick a distance to ensure that there are no isolates or no islands. We take the max-min distance, the largest nearest neighbor distance. Okay, what does this look like? This is Solano County again. Recall the difference with the contiguity. These are the rook and queen neighbors. If we take the max-min distance for counties in the US, that is 90 miles roughly, then we have a much larger band of neighbors for Solano County. This will matter down the line when we look at the spatial autocorrelation statistics and interpret the difference between them. Okay, this critical distance is actually pretty critical, and this is my favorite example. Elko County, Nevada. I've actually driven through there several times. Elko County, just as an aside, is known as a gold mining town. It's in the middle of nowhere, and this is reflected in this example. So if we take the critical distance of 90 miles from the central point, from the centroid of Elko County to the central points of all the other counties, it has exactly one neighbor. Right? If we, and this is Idaho up here. So this is in the direction from Nevada to Idaho in the US. So one neighbor. However, if we pick 80 miles, let's say we're interested in looking at commuting patterns and we find some article that says the average commuting distance is 80 miles, let's take that as our critical distance. Elko County has no neighbors whatsoever. In other words, if we take the distance, the critical distance, as 80 instead of 90, then Elko is an isolate or an island. So that's something to keep in mind when you use distance-based weights, and we'll revisit that when we look at the characteristics of weights in a little bit. Then there's a kind of a solution. It's not really a solution, but it's a way to avoid the island or isolate problem, is rather than taking a given critical distance to define the neighbors, you say, well, I'll take whichever are the k closest, the k nearest neighbors. Now, that means that we ignore distance. We say, we don't really care how far apart they are, as long as they're, say, the 4 nearest neighbors or the 6 nearest neighbors. Now, with a dense distribution, the nearest neighbor distance will be very small. With a sparse distribution, the nearest neighbor distance will be very large. So implicitly, we're saying that we have a flexible distance decay phenomenon. In other words, what we're saying is that in a dense distribution, the distance decay is much steeper than in a sparse distribution. Think about this. If you live in a city like Chicago, you might just think about walking to the grocery store. And so then any grocery store that's more than, say, 15 minutes walking from where you live is too far. But if you live in Wyoming, you don't mind driving 45, 50 minutes to the nearest grocery store. So it's still the nearest grocery store, but the distances are very different. So that's the kind of implication that you have when picking k nearest neighbor weights. Now, the easy thing with k nearest neighbors is that every observation has k neighbors, except in practice we might have problems with ties. So if you have a location and 2 locations that are equidistant, or an equal distance apart, and say neighbor number 4 and number 5 are the same distance apart, and you do 4 nearest neighbors. Which one of 4 or 5 do you pick? They're exactly the same distance apart. And so in practice, you have to deal with this. You can't ignore this. In theory, you can ignore it, but in practice, you cannot. So what we do in GeoDa, we randomly pick one or the other. Some other approaches are to include all of them, but then you break the k. So then you would say, okay, I'll take 4 and 5, but then for that observation, there's actually 5 neighbors, not 4. So then the k is violated, and that's why we randomly pick one or the other. But these are the kinds of things you think about when you do actual data analysis, actual data science. K-nearest neighbors can look very strange. Here we're back with Elko County. Look at the 4 nearest neighbors. They don't include, say, this one or that one. They are based on the distances between the centroids of the polygons. So that can lead to arrangements that are not very intuitive. For example, in this case, all the neighbors are kind of at the northeastern part, and there's no neighbors on the west side of Elko County. So these are the kinds of things we, in the lab notes and in practice, we pay very careful attention to, and that's also why we look in a few minutes at the characteristics of the weights to try to pick up situations where these kinds of strange artifacts might be occurring. So far, we've thought about the spatial weights as binary weights, 1, 0. Typically, we don't use them that way. And one important concept is a concept of row standardizing the weights. And people are often confused by this in the beginning, but it's just a rescaling of the weights. And the rescaling has a lot of advantages. For one, it makes all the weights comparable. So we no longer have to worry about, my identification problem. Interaction is a problem. We have a coefficient times weights. If the weights are large, the coefficients are small, and vice versa. If we scale the weights so that the row sum, so the sum of all the weights for every observation is 1, then all of a sudden the weights become comparable. Then all of a sudden the coefficients become comparable. So that's a major advantage. And in practice, that is typically done, especially in an exploratory analysis. So formally, we make sure that the sum over j, meaning for every observation I, j are all the neighbors, the sum over all the neighbors of the weights equals 1. And then how do we get there? We get there by dividing each of the original weights by the row sum. So we divide our original weights by the row sum, and then we get a rescaled weight so that they're all in the same order of magnitude. Makes the analyses comparable, makes the correlation coefficient comparable. It also leads to a concept that we'll actually be using in the next set of modules, the concept of a spatial lag, or a spatially lagged variable, which is simply an average of the neighbors. And we get that average for the neighbors by using row standardized spatial weights. What does this look like? For our little example, the first row we have 3 neighbors. So the sum of the row elements is 3. And as a result, our rescaled weights are 1 over 3. In the third row, however, we only have 2 neighbors. And so then the weights are 1/2. And in the fifth row, we have 4 neighbors. So then the weights are 1 over 4. So look what this does to our symmetry of the matrix. Remember, we had very nice first row and first column were exactly the same in terms of zeros and ones. Here, we're fine. Here, we're not fine. So the row standardization breaks the symmetry of the spatial weights. And that's something we will have to keep in mind later on when we deal with the comparison of the statistics. But other than that, very simple operation. You figure out the sum of the weights for each observation, and you divide the weights by that sum, and as a result, they all scale nicely to 1. There's another side effect, benefit, if you wish, of this. In many statistics, we will need the sum of all the weights. Now think for a second. When we row standardize the weights, we always immediately know what the sum of all the weights is. because the sum of the weights in each row is 1 by construction, and we have n, the number of observation, such rows. So as a result, the sum of all the weights in the weights matrix for a row standardized weights matrix is exactly the number of observations, n. And that will come in handy later on as well. Then there's a second operation that we need to be aware of. It's the notion of higher order weights. And this is actually kind of complicated because it is a so-called recursive working backwards definition. So you define a neighbor of order k, let's say, as a first order neighbor of the neighbors of order k minus 1. So what is a second order neighbor? It's a first order neighbor to a first order neighbor. What is a third order neighbor? It's a first order neighbor to a second order neighbor. And so this is how we define higher orders of neighbors, further and further out. Now there's a problem with this, in that lower order neighbors are also oftentimes higher order neighbors. I'll illustrate this in a second. So we don't want duplication. So in time series, think of time series. When you say an observation is 1 year ago, you know exactly when that was, versus when it's 2 years ago, you know exactly what that was. And an observation that's 1 year ago cannot also be 2 years ago. In space, it's different. An observation that's a first order neighbor, meaning 1 year ago, in quotes, can also be a second order neighbor. So it's both 1 year and 2 years away. That's not good. For some analyses, that's terrible. For other analyses, it's not such a big deal. So for those analyses where it does matter, we need a pure notion of higher order contiguity, which means that we need to eliminate the neighbors that double dip. So if you are a neighbor of order 1, you cannot be a neighbor of order 2. If you are a neighbor of order 2, you cannot be a neighbor of order 3. So we need to keep that in mind when creating higher order weights matrices. So we have both this pure notion, as I said, when we really care about it, pure notion of higher order contiguity. And then we have also what I call a cumulative notion of higher order contiguity, where we actually include all the lower order neighbors as well. So you can think of that. So the pure order, you can think of like a donut, and then another donut bigger, and then another donut even bigger. Cumulative contiguity, you start with a ring, and then the ring just gets wider and wider and wider and further away from the original observation. Okay, let me show this. So first of all, the pure notion. So observation 4 and 3 are first order neighbors to observation 5, which is a first, let me rephrase that. Observation 3 is a first order neighbor of observation 5, which is a first order neighbor to observation 4. So in the recursive definition, we have 5, 2, and 1 being the first order neighbors of observation 4. 3 is a first order neighbor of those first order neighbors. So 3 becomes a second order neighbor. 6 is a first order neighbor to 3, which is a second order neighbor to 4. So 6 becomes a third order neighbor. You can also think of this as the number of steps you have to take in the graph representation. So here's our graph again, our different nodes. To get from 4 to 3, you need 2 steps to get there, the shortest steps. You can also go in 3 steps, and this illustrates my point, which I'll get to in a second with another. So the shortest steps is to 5 and then to 3. The longer steps is to 2, to 5, and to 3. So that would imply that 4 and 3 are third order neighbors, but they're not, because they're already second order neighbors. So that's what I mean by the pure definition. Let's look at this a little more closely, and let's look at all the paths in the network between our node number one, our cell number one, and all the other cells. And here's something you might not have thought about, but remember, I am my neighbor's neighbor. So if you go from 1 to 2 in one step, you go back in another step, and there's our 2 steps. So 1 is a second order neighbor of itself. 2 is a second order neighbor of 1 if we go via 4, or if we go via 5. Now these are all 2, 4, and 5 are all already first order neighbors, so they don't count. The only one that truly counts is 3, which takes 2 steps to get to from 1. So that's this notion of pure contiguity, removing the redundancy, versus cumulative contiguity, which does not. What does this mean in practice? Back to our Solana County. So on the left, we have the pure second order contiguity, in the sense that our first order queen neighbors, if you recall these here, are eliminated. Whereas in the cumulative contiguity, they are included. So that's the difference between the two. Which one to use? If you're using formal modeling, often this makes sense. In an exploratory analysis, I would say the cumulative analysis makes a lot of sense. Oftentimes, I see that in your assignments and in the past when we did projects, people would use the pure second order contiguity, but and then it's interpreted as if it was cumulative. So you're fine to use the pure contiguity, but then you have to interpret it as pure contiguity and not include the first order neighbors in your interpretation. That's something to keep in mind for later. Okay, so we have row standardization, we have higher order contiguity. How can we tell these weights apart? So we have a couple of descriptive statistics for the weights that characterize them in terms of their density, in terms of the distribution of the cardinality, which is the number of neighbors, and so on. The simplest one is what I call, a lot of these have been developed originally for GeoDa. Some of them are unique to GeoDa, some of them are fairly common. A connectivity histogram is really a histogram of the number of neighbors. In other words, we look at how many observations have 1 neighbor, 2 neighbors, 3 neighbors, 4 neighbors. That is the basis for the histogram. It gives the distribution of what we call the cardinality of the neighbor cardinality, how many neighbors there are. And this is really useful to find out whether we have a problem with isolates. Remember the isolates I mentioned earlier, those are observations that don't have a neighbor within the given distance band. So they're just floating there alone in space. And there's some other characteristics of the distribution I illustrate in the lab notes when you have situations of bimodal distribution. Some observations have very few neighbors and others have very many. So what do we use this histogram for? We, first of all, try to spot if there are isolates or islands. And as I alluded to a few minutes ago, what do we do with these islands? So since spatial analysis is about spatial interaction, and they don't interact, they don't play. So you should remove them from spatial analysis. But if you're not interested in the spatial aspects, if you're just interested in the standard aspects of the distribution of the data, by all means they should be included. So it's not a one-size-fits-all type of recommendation. The other thing to watch out for is for too many neighbors. Remember earlier on I alluded to the fact that in an exploratory analysis we want to constrain the number of neighbors to a small number of neighbors to really be able to pick up whether there is some evidence of non-spatial randomness. And we pick that up much better when we have a very small number of neighbors. So if we have situations where there are lots and lots of neighbors, that is not good. Also, a bimodal distribution. What's a bimodal? I already mentioned. Some observations have very few neighbors and some have very many. And in the lab notes, I actually give an illustration. In the state of Virginia in the United States, some counties are city counties and other counties are just regular counties. A city county is surrounded by another county. So all these city counties only have one neighbor, the county that actually contains them. And all the other counties have a regular number of neighbors, in the US around 5 or 6 on average. So that gives you a bimodal distribution, which is something you should watch out for because it will affect what your spatial autocorrelation measure picks up. So in GeoDa, there are these summary measures. They tell you the type of weights, whether they're symmetric or not. These items are detailed in the lab notes. But here, minimum number of neighbors, maximum number of neighbors. Queen, because it includes the corners, will always have more neighbors than rook. And we see that here by the maximum number of neighbors, and also the average number of neighbors is slightly larger for queen than for rook. But as I mentioned before, there isn't a big difference between the two in most situations, except on a regular grid. So then, this is our connectivity histogram. It just gives you, for both rook and queen, that the mode, the maximum, the largest number of observations that have that number of neighbors, 6, is for US counties. Okay. This is what this looks like when we use a distance-based criterion. Remember, we came up with our max-min distance of 90 miles for US counties. This gives you the range of number of neighbors. Some counties using that measure have almost 90 neighbors, and some have just 1, like our Elko County, right? So what happens when we go to 80? Then we get a warning. 5 observations don't have a neighbor, including, as we know, Elko County. So that's something to look at in these connectivity histograms. Then, for k nearest neighbors, it looks like this. Why? Think about it for a second. K nearest neighbors. Every observation has k neighbors. The connectivity histogram is meaningless for k nearest neighbors. However, other characteristics are not meaningless. And most importantly, and this is often extremely useful, is, as we've already seen, we can represent contiguity as a graph structure, as a network, where the observations are the nodes, and the presence of a common border of contiguity is an edge. And in our simple example with 6 observations, that was a nice, clean little graph. For the US, it's a little more complicated. So this is the graph network structure of contiguity based on queen contiguity for US counties. And what do you use this for? Well, you look for aberrations in the system. And one thing, for those of you who are not familiar with the US, one thing to realize is that basically east and west of this line, this is a much denser network than west of the line. In other words, these counties out west are much larger, a much sparser distribution. The counties out here in the east and in the Midwest have a much denser distribution. So in the lab notes, there's some illustrations of how you use this kind of information to assess the quality of your spatial weights. So what we saw in this second set of slides, it was very practical. First of all, the big conceptual jump is how do you quantify the existence of a neighbor relation, and we do that with the spatial weights. We saw an easy way to define them by means of geography, contiguity, or distance. We row standardize the weights in order to make sure that they're comparable, and then we can assess their characteristics by means of this connectivity histogram or the network structure. In the lab notes, there's some other examples. There's a connectivity map that you can explore to find the different neighbors for observations. So this kind of concludes our discussion of spatial autocorrelation generically. In the next module, we'll address specific spatial autocorrelation statistics and how to visualize them.